Welcome back, AP Calc. This is the second part of the notes on computational continuity. We examined a lot, but we didn't examine trig, and that's what we're going to do now. So if you check out sine of x, I think the best way to talk about it is just to look at its graph to start with. If you recall, sine of x started at 0, 0. If you went over pi over 2 units, every pi over 2 units, a regular sine function would move up to a unit of 1. So I'll just call this 1, and each of these a pi over 2. It's kind of like on the unit circle how sine is 0 here, then it's 1 there. Now it's back to 0. Now it's down to -1. Now it's back to 0. And it just keeps cycling like that. You go backwards to -1, to 0. Based on what we've seen with other continuous functions, there's not really a huge difference. There's no holes in the graph, there's no breaks, there's no asymptotes. Sine of x is continuous everywhere. Which, of course, if you know what sine of x looks like, you can literally just say, hey, here's cosine. And instead of, you like what I did there? Cosine starts at 0. Starts at 1, goes down to 0, down to -1, and pretty much does the exact same thing. It has the same kind of behavior in terms of its domain. So, sine's continuous everywhere. Cosine's continuous everywhere. But that's kind of where it stops as far as the continuous party goes. Because every other trig function can be written in terms of sine and cosine, always with one of those on the bottom of a fraction. Tangent, for instance, can be rewritten as sine of x divided by cosine of x. Which means we have a domain issue wherever cosine of x equals 0. If you recall from your unit circle days, cosine is the same thing as the x value on the unit circle. So on the y-axis, cosine equals 0. So when we're at pi over 2, 3 pi over 2, 7 pi over 2, and so on, which can be written as at x equals pi over 2 plus pi n, where n is any integer value, you've got domain issues. So how will we talk about this? Well, for tangent, we would say tangent of x is non-removably discontinuous. I'll just, for time purposes, say NRD. At x equals pi over 2 plus pi n. Continuous every other point. So you could extend this to the three other trig functions. The inverse, not the inverse of sine, but the reciprocal of sine would be cosecant. The reciprocal of cosine is secant. And then the reciprocal of tangent is cotangent. Doing a quick rewrite of all of these, this is 1 over sine. This is 1 over cosine. And this is cosine over sine. So the domain of tangent and the domain of secant are connected because they both have a cosine in the bottom of their fractions. So secant basically piggybacks on this concept of I can't have cosine equaling 0, so we are also going to be non-removably discontinuous at x equals pi over 2 plus pi n. And then you're just doing the opposite for cosecant and cotangent. You're saying sine of x is equaling 0 is going to be the spot where you have asymptotes, which make them non-removable discontinuities. Sorry, I don't think I explained exactly why they were non-removable, just because, hey, they're discontinuities that can't cancel out. And if you recall, tangent, oh yeah, I was using this graph over there. Sorry. Yeah, tangent looks kind of like this, where at pi over 2's, you got asymptotes. So every pi over 2, there's an asymptote. For cotangent, it's the opposite. Basically, here and here are where you have sine equaling 0. Remember, sine represents the y value. So if you're on the x-axis, your y is equal to 0. Sine can't be 0 on the bottom part of a fraction without creating a domain issue. So at pi n, 0 plus pi, plus pi, plus pi. 0 plus pi n, which is pi n, that's where you're going to be non-removably discontinuous. So cosecant is non-removably discontinuous at x equals pi n, and so is cotangent. So let's see how we can apply this to certain situations. So here's our first two examples. You've got a cosine function that has inside of it nested a rational function. Yeah, you can see that better now. Now for the cosine itself, there's no issue. Inside here, though, x cubed minus x cannot be 0. So we're going to have a few discontinuities here. So I'm going to expand this out a little bit here. You can take out an x, leaving you with x squared minus 1. Difference of squares factoring, which leaves you with x minus 1, x plus 1. All right. So what this demonstrates to us is that you can still have removable discontinuities within a trig function, but it has to follow the same rules that it did when we were dealing with the other fraction rational functions. So no issue with the cosine, but we have a removable discontinuity at x minus 1 equals 0, which is the same as x equals 1. And we have non-removable discontinuities at the asymptotes, which are at x equals 0 and x plus 1 equals 0. We just call this one negative 1, though. It's the thing that makes it 0. Yeah. Number 10 is a little more complex. First thing I would do is turn it into terms of sine and cosine. So cotangent is equal to cosine of the x plus 3 over sine of the x plus 3. Notice everybody got the x plus 3. I didn't just morph it into some cos over sine and then put an x plus 3 beside it. You need two separate x plus 3s. So here's the deal. There's no domain issue with cosine or sine when you put a polynomial inside of the parentheses. It's sort of the angle for it. But the bottom still can't equal 0. And this is kind of a tricky thing. What we're saying is that, you would normally say sine equals 0 at x equals pi n, all right? So now we're saying sine of x plus 3 equals 0 at x plus 3 equals pi n. See, all I did was say, hey, you got an x here, that's the x here that equals pi n. Well, if it's x plus 3, I'm just going to replace it where I saw it in that statement there. Hopefully that makes sense, which all you got to do at this point is subtract the 3, get x by itself. So, at x equals pi n minus 3, we have non-removable discontinuities. And of course, they're non-removable. Ooh, excuse me. They're non-removable because we couldn't divide out the domain issues that remain there. All right, we're to our last two functions. Sorry. All right, last two. And they're very rich. There's a lot to learn from them. So on our top one, number 11, we got a rational function where it says 1 plus the secant of x divided by secant squared of x minus 1. So this has several issues. The first being that there's a secant in there. All right? So the instant you see the secant, you're thinking to yourself, hey, secant of x equals 1 over cosine, which cosine at the bottom, bad news. You instantly have non-removable discontinuities at x equals pi over 2 plus pi n. There could be more, but I know for sure that there's going to be some at pi over 2 plus pi n. Now, if you notice the structure of the denominator, it looks like a difference of perfect squares. You could take secant of x times secant of x to get this. You take 1 times 1 to get this. So we can actually split it up using that factoring strategy. I'm going to rearrange this so that you got the secant of x first. So this is going to be secant of x plus 1. I'll use brackets here because I already put parentheses there. Times secant of x minus 1. Hopefully the brackets aren't confusing. I'm just using them as parentheses at this point. All right, so this quantity, they divided each other out, which means we have removable discontinuities at secant of x plus 1 equals 0. So it's been a little while since we solved trig equations. The secant of x equals negative 1 can be rewritten as cosine of x if we flip both sides of the equations. So if I flipped secant, I get cosine. If I flip negative 1, I still get negative 1. That's pi, okay? Cosine equals negative 1 at pi. So we know that we have removable discontinuities at x equals pi. And if we're talking all solutions throughout the entire span of this function right here, you'd say plus 2 pi n. And we're still not done because this is still existing on the bottom part of the fraction. It's a non-removable discontinuity because it was not canceled out. Which we can add it to both sides, the 1. And do that same move, you know, it's like, hey, if I flip secant, I get cosine. If I flip 1, I still have 1. Yeah, and when you think about the unit circle again, sorry if I wasn't clear on this one why it was pi. The unit circle says hey, cosine equals 1, the x value equals 1 over here, which is 0, 2 pi, 4 pi, 6 pi. It's 2 pi n, 0 plus 2 pi n. So I have non-removable discontinuity at 2 pi. I guess I should put it up here. 2 pi n. Yeah. Okay. All right. This film is up to 15 minutes or so. I think we have time for 12. Last one. All right. It's kind of a dandy here. You got a square root. You got a square inside, and it's cosecant. So the first thing you can state right off the bat is, cosecant's always getting in all kinds of domain issue trouble. Cosecant of x equals 1 over sine. So I know right away, instantaneously, that there's a non-removable discontinuity pattern at x equals pi n. Just from that. We also know that if it's a root, then the inside of it needs to be greater than or equal to 0. So how do we solve something like this? I mean, I could subtract 7 from both sides. The subtraction property of inequalities. You guys learned that back in Math 1. But beyond that, it's kind of like we're stumped. I don't want to try to square root both sides. Oh, wait. Look at this. I'm squaring a quantity. Any quantity squared, at least in the real number system, is going to yield a positive value. When is a positive output, okay? Positive number on the left-hand side always. When is that going to be bigger than negative 7? Always. There's an infinite number of solutions to this equation, this inequality. This inequality is basically stating, throw in any x you want. It's still going to be greater than negative 7. Always. Always going to be greater than or equal to negative 7. So what that does is it says, hey, we got no more domain issues, but we still need to take into account the fact that there's a non-removable discontinuity pattern at x equals pi n. All right, guys, I hope you found this video helpful, and thanks for watching.